Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it.
This is chapter 5.5, which is integration by substitution. Now, integration by substitution is more commonly known as U-sub, alright? And let's recall something here. Recall the chain rule. And what was the chain rule? The chain rule was the derivative with respect to x of f of g of x was equal to f prime of g of x times g prime of x, right? We want to keep that in mind as we go through integration by substitution. So, theorem. Because here the U substitution is essentially the chain rule going backwards for integrals, all right, so that we can find integrals. So, anti-differentiation of a composite function. All right, and that's essentially, again, just known as U sub. So, let G be a continuous function whose range is an interval I, and let F be a function that is continuous on I. Alright, so f is continuous on the range of G. Alright, if G is differentiable on its domain, and capital F is an antiderivative of lowercase f on that interval, then we get the following. So G is continuous and its range is I. F is continuous on that I, on that interval I. G is differentiable in its domain, and f is an antiderivative. So if G is differentiable in its domain, and f is an antiderivative of lowercase f, then we get the following. The integral of f of g of x times g prime of x dx is equal to capital F of g of x plus t. Alright? Now this is more commonly written as the following. So we're going to say if we let u be equal to g of x, then that tells us that if I take the differential here, du will be equal to g prime of x dx. Notice here that g prime of x dx is our du, and that g of x here is our u. Right? Here's our u as well. So if we let that happen there, well, we can rewrite this integral as the integral of f of u du is equal to capital F of u plus c. Alright? So this is a very common integration technique, alright? Doing this integration by substitution. And again, it is essentially doing the chain rule backwards. Alright? Now, let's do some examples here. Let's say that I have the integral of 8x squared plus 1 squared times 16x dx. Right? And here, what we want to do is we want to put into this format, into U sub. Alright, we want to figure out how to do that here. And The way we do that is, well, we gotta let something in here be u. And here's the way that we decide this. Essentially, what we're gonna look at is you want to look at the pieces all over the place here and see which one is the derivative of the other, or which one is sort of like the derivative of the other. Now, in here, if you look at this 16x and you think about this piece inside here, the derivative of this piece inside here is 16x. So this part is what I'm going to let my u be. So I have 8x squared plus 1. At that point, du would be the differential of this. So that would be 16x dx. And at that point, notice that we have this 16x ds here and that 16x dx there. And our u was this piece, right? So what we can do now is we can rewrite this now as the integral of u squared du. Alright? And at this point, well, now we're integrating with respect to u. So the integral here would be u cubed over 3. And because it's an indefinite integral, we do plus c. But one thing to keep in mind here, as we're doing all these u subs, is the original problem. What was the original problem? It was this stuff. And the original problem was in terms of x. Alright? So we want to make sure that we put everything back into terms of x. In other words, the problem was not about u. It was about your x over here. Alright? So replacing that, well, what was u? U was 8x squared plus 1. So this gives us 8x squared plus 1 cubed over 3 plus c. Alright? Next one. B. Let's say we had the integral of the square root of 25 minus x squared times, let's just do 2x dx. Alright, so now let's see. What piece kind of looks like the integral of the other piece? Alright, well, in here, I see here, well, if I let u be this piece, right, the derivative of this is sort of like this, right? The derivative of this is just negative 2x. This is almost like negative 2x. It is 2x, but it's not negative. So what we can do is, let's start with that. Let's take that u to be either 25x squared. At that point, taking the differential, I end up with negative 2x dx, right? And while we do have a 2x dx there, we don't have that negative. So what we can do is we can move this to the other side. So I end up with negative du is equal to 2x dx. And now I can easily replace that entire piece there. Alright? Alternatively, well, actually, you know what? I'll show the alternative after we're done with this version. What we get now is, well, 25 minus x squared, that was our u. So we have u. Instead of writing square root, I'm going to write it to the power of 1/2. That 2x dx was our negative du. So we have this times a negative du. This negative, we could put it on the outside. So I have negative integral of u to the 1/2 du. And what does that give us? Well, we have negative, add 1 to the exponent, u to the 3/2, divide by the new exponent, but we're dividing by a fraction, so we can multiply by the reciprocal. And then we have that plus c. But recall that the problem was not about u. So what we have here is negative 2 times 25 minus x squared to the 3/2 over 3. Right? Make sure the problem is always in your x over here. Alright, so I said I was going to do an alternative to this. So let's do this problem again. Let's say that I had, so it was the integral of 25, the square root of 25 minus x squared. Alright, dx. So let's see. We started the same way. U is equal to 25 minus x squared. Oh, hold on. I missed something, didn't I? Yep, the 2x. 2x dx. There we go. Way better. Now, I still start with u being 25 minus x squared, and then du was negative 2x dx, right? In here, what we can also do is we can solve for dx. So what would dx be equal to? Well, we would have to divide this side by negative 2x. So I end up with du over negative 2x. At this point, what does this integral become? Well, let's see. We want to replace as many things as possible. This 25 minus x squared, that was our u. So u to the 1/2, right? Because instead of square root. All right, cool. This 2x we did not use for our substitution, so I'm going to write it again. dx was du over negative 2x. At that point, you see that the 2x's cancel each other out, and what we really have here is, well, this negative, I can take it to the outside, so negative integral of u to the 1/2 du. And now we're back at this step, right? So we already know what the final answer is, so I won't finish it from here. But the point here is that we can solve for dx here, so that we don't have to worry about looking for this piece, the du, on this side up here. All right. Let's look at another example. So that was B. C. Let's say that I have the integral of 7 secant squared of x times tan of x plus 3 dx. Alright? Alright, so now, let's see. In here, what do we have? We have a tangent and a secant squared. If you recall, the derivative of tangent is secant squared. So I'm going to start here by saying u is equal to tangent of x. But in fact, I can take this 3 with it. Why can I do that? Well, because the derivative of that, our du, our differential, would just be secant squared of x dx. So in other words, it doesn't affect our du. We're still going to be able to take that secant squared. And now, at this point, well, I'm going to do this by solving for dx. So I have du over secant squared of x. And at this point, let's see. Well, what does our integral become? We have the integral of 7 times the secant square x. We did not use that for our substitution, so it's still there. Times tan x plus 3. That's our entire substitution. And then dx was du over secant square of x. At this point, we see that secant squared and secant squared cancel each other out. So what we have here is just the integral of 7u du, giving us 7u squared over 2 plus c. But u was tangent of x plus 3, right? Never leave the problem in terms of u. So we have tangent of x plus 3 squared over 2, and then that plus c. All right. Next one. D. Let's say I have the integral of 5e to the negative 3x dx. Alright. So in here, well, let's see. I don't know what the integral of negative 3x is. We haven't spoken about that. But if I let u be equal to negative 3x, notice that du would just be negative 3 dx. And even though I don't have that negative 3 anywhere in here, well, I also don't have any variables that I need to undo it. So what we can do now is make dx be du over negative 3, so that this integral now becomes the integral of 5 times e to that negative 3x is our u, so e to the u. Instead of dx, I've got du over negative 3. So essentially I have negative 5/3 times the integral of e to the u du. And at that point we say, well, the integral of e to the u is just e to the u, so I have negative 5/3 e to the u plus c. But we know the problem is not about u. Never leave it in terms of u. So negative 5/3 times e to the negative 3x plus c. That would be our integral there. All right. Next one. E. Let's say I have the integral of x cubed times x to the 4 plus 3 squared dx. Alright, well, what piece looks like the derivative of the other? Well, this piece looks like the derivative of that piece. So I'm going to say, well, let u be equal to x to the 4 plus 3. Then du would be 4x to the third dx. Then dx would be du over 4x to the third. And at that point, we can say that our integral becomes the integral of this x cubed. That was not part of my substitution, so it's still there. Times this x to the fourth plus 3. That was my substitution. So u squared, and instead of dx, we've got du over 4x cubed. At that point, we see that the x cubes cancel each other out, and we end up with the integral of, well, 1/4, right, because of this 4. 1/4 integral of u squared du, giving us 1/4 times u to the third over 3 plus c. But the problem was not about u, so put it as x to the 4 plus 3 cubed over 4 times 3, which is 12 plus c. Right? Next one. Let's say I have the integral of t times the square root of t squared plus 2 dt. Alright, and here, we're using some other variable here, t, but we can still do a u substitution, right? And again, I'm looking for what looks like the derivative of the other. Well, this is a quadratic inside here, this is linear, so the quadratic's derivative is linear, so I'm going to make the quadratic be my u. And at that point, my differential would be 2t dt, which tells me that dt is equal to du over 2t. So at this point, I say, well, this integral becomes this t. I didn't use it for my substitution. This t squared plus 2, that was my u. The square root is to the power of 1/2. This dt is du over 2t. At that point, we see that this t and that t cancel each other out. So what we really have here is just 1/2 times the integral of u to the 1/2 du, which is 1/2 times u to the 3/2, right? Add 1 to the exponent, divide by the new exponent, which is multiplied by the reciprocal, plus c. At that point, these two cancel each other out, so I have, instead of u, we have t squared plus 2, right, over 3, and then this is to the power of 3/2 plus c. Cool. Next one. G. Let's say we have the integral of x to the third over 1 plus x to the fourth squared dx. If you notice here, there's 1 plus x to the fourth. Its derivative is something like that. So if I make u be my 1 plus x to the fourth there, then my du becomes 4x to the third dx. Right? And at that point, I can say there that dx would just be du over 4x to the third. At this point, we'll say the integral becomes, well, that x to the third, that wasn't part of my substitution, it's still there. This 1 plus x to the fourth, that's my u, so u squared. This dx, that's our du over 4x cubed. At that point, we see that the x cubes cancel each other out, so we end up with 1/4 integral of 1 over u squared du. And we can rewrite that now as 1/4 integral of u to the negative 2 du, giving us here a quarter. We'll add 1 to the exponent, divide by the new exponent, plus c. Well, we can rewrite this now as negative 1 over 4u plus c, but the problem was not about u. So it was about 1 plus x to the fourth. So 1 plus x to the fourth plus c. Cool. Next one. H. Let's say that I have the integral of x times the square root of 2x minus 1 dx. Alright. Well, in here, the derivative of the inside is not that, and the derivative of this is not that inside either. So this is kind of tricky as to how we choose our u. But here's what we're going to do. This entire inside part, let's make that our u. Let's see what happens. U is 2x minus 1. Then at that point, du would be 2 dx. So telling us that dx is equal to du over 2. Alright, so what does this become now? That tells me now that we have the integral of, we didn't use our x for our substitution, right? So x times the square root, well, I'm going to write to the power of 1/2. Instead of 2x minus 1, that was our substitution, so that's our u. Dx is du over 2. Look at that. Now this is a problem. This is a problem because we have x's and u's. Alright? U don't mix with x. Alright? U does not mix with x. So what we have to make sure that we do here is put everything in terms of u. Alright? Right now we need to put everything in terms of u. So how do we do that? Well, let's look at this over here. From here, if I solve for x, add 1 to both sides, so I have u plus 1, and then divide by 2, so over 2. That's going to be equal to our x there, u plus 1 over 2. Alright? So what we say now, well, now we can replace our x. So we have here u plus 1 over 2 times u to the 1/2 du over 2. Alright? And now let's see what we can do here. I'll put the u plus 1 in parentheses. I have a 1/2 here, 1/2 there. We can take it out and it'll be 1/4. And now u to the 1/2 times u, that's u to the 3/2. U to the 1/2 times 1, that's u to the 1/2. And we have all of this du. Alright? And at this point, well, let's see what we get. We get 1/4 times the integral, times the integral of u to the 3/2. We'll add 1 to the exponent, divide by the new exponent, but it really means multiply by the reciprocal of it, plus u to the 1/2, we'll add 1 to the exponent, divide by the new exponent, which really means multiply by the reciprocal of it, plus c. But the problem was not about u. It was about our x over here. So what we have here is 1/4 times 2x minus 1 to the 5/2 over 5 plus 2 times 2x minus 1 to the 3/2 over 3 plus c. Alright. And that would be our final answer. If you really wanted to, we can, I guess, distribute the 4. I won't. I'll leave it as that. Next one. What was that? H? So I. Let's say that I have the integral of sine cubed of x times cosine of x dx. Alright? Now, let's think about this one. We've got two pieces, sine to some power and cosine. The derivative of sine is cosine. So that's how I'm going to start this. We're going to say, well, let u be equal to sine of x, then du would be equal to cosine of x dx, so that dx is equal to, well, you know what, and this one is not that difficult to see. Cosine of x dx, that's our du. So we have now, we end up with the integral of u to the third, right? Sine of x was my u, and then cosine of x dx, that's du. And this gives me now just the integral, the integral of u to the third gives me u to the fourth over 4 plus c, and u here was sine, so I have here sine to the fourth of x over 4 plus c. Alright. Now, I cut out example J from this video since it required knowing an integral that we had not yet spoken about. So that you will see that kind of integral in the next video of 5.7. Alright, so now back to the regularly scheduled programming. Okay. Let's say that we had the integral of e to the tan of x times secant squared, and I didn't want tan of x. I wanted to do tan of 2x times secant squared of 2x dx. Alright, so in here, let's see what we can do. If I let u be this entire exponent over here, right? Because I know that the derivative of tangent is secant squared, so I want to use this. So if u is tan of 2x, then du would be equal to the derivative of tangent secant squared, and then by the chain rule times the derivative of the inside, so times 2 and dx. Alright, so that's our differential. And then dx would be, well, du over 2 secant squared of 2x. Right? And at that point, well, we can rewrite this. Now we can say here we have the integral of e to the tan of 2x, that was our u. So e to the u, secant squared of x, supposed to be secant squared of 2x, we did not use for our substitution. Dx, that's du over 2 secant squared of 2x. At that point, we see the secant squared of 2x cancel out, so we end up with just 1/2 times the integral of e to the u du. Write this 2, put it in the outside, and the integral of e to the u is just e to the u plus c. And the problem was not about u, so we got to put it back into the terms of the original variable. So we have 1/2 e to the tan of 2x plus c. Alright, and that would be our final answer. So that was K. L. Let's say that we have the integral of e to the negative x times secant squared of e to the negative x dx. Alright, so in here, well, I'm going to let u be e to the negative x. So what would my du be? Du would be negative e to the negative x dx. So at that point, my dx would be du over negative e to the negative x. But what was e to the negative x? That was our u. So here I can rewrite this as du over negative u. Alright, and then what does that do for us? Well, we can say now we have the integral of e to the negative x. That was our u. So I have u times secant squared of e to the negative x, which again was our u, and dx, which was du over negative u. At that point, we see that the u's cancel each other out, and we end up with the negative integral, right, negative because of this one, of secant squared of u du. And the integral of secant squared, well, the derivative of tangent is secant squared, so the integral of secant squared will be tangent. So we have negative tangent of x, not x, our variable was u. We're doing things in terms of u. So negative tangent of u plus c. And at that point, u was e to the negative x, so we have negative tangent of e to the negative x plus c. All right, and there we go. So that was L. M. Let's say that we had integral of, let's do x squared times the square root of x cubed minus 2 dx. And here, this inside part, that's going to be our u. So let u be equal to x cubed minus 2. That gives the du to be 3x squared dx, right? And that's why I chose my inside to be our u, because I saw this x squared out here. So at this point, dx would be du over 3x squared. So now our integral becomes, well, this x squared, I didn't use it for anything. This square root, I want to write it to the 1/2. This x cubed minus 2, that was for u. This dx was du over 3x squared. And at that point, you see that the x squares cancel each other out. So we end up here with the integral, well, 1/3 times the integral of u to the 1/2 du. So we end up with 1/3 times, add 1 to the exponent, u to the 3/2, divide by the new exponent, which is multiplied by the reciprocal, plus c. And from there, what does that give us? That gives us, well, 3 times 3 is 9, so we have 2 9s. The problem wasn't about u, so we can replace it with x cubed minus 2 to the 3/2, and then we have that plus c. Alright? So that was m. N. Let's say that we have here the integral of sine squared of 3x times cosine of 3x dx. Alright? In here, well, let's do this. In general, I don't really like to have those 3x's like that, the arguments of sine and cosine be things like that. So I'm going to start with a u substitution, but instead of u, I'm going to call it theta. Alright, so I'm going to call it theta just for the purposes of remembering that the input of sine and cosines are supposed to be angles. So theta, I'm going to let it be 3x. Therefore, d theta would be 3dx, giving us that dx would be d theta over 3. Alright, now, what does this look like now? It looks like the integral of sine squared of theta times cosine theta times d theta over 3, right? The 3x was our thetas, the dx became d theta over 3. Alright, so now, let's say that, well, we have here a product of sine and cosine. Because cosine is a word that doesn't have the exponent, I'm going to make sine ru. So let's say that u is sine theta. Then du would be cosine theta d theta. So that d theta is du over cosine theta. And at this point, what does this give us? This gives us the integral of sine, that was for u. So I have u squared times cosine, we didn't use that inner substitution. So there's cosine theta. This 1/3, I'm going to put it on the outside, and this d theta was du over cosine theta. At that point, we see the cosine thetas cancel each other out, so we end up really with just 1/3 times the integral of u squared du, and that would just be 1/3 times u cubed, right? Add 1 to the exponent, divide by the new exponent, so u cubed over 3 plus c. And then 1/3 times 1/3, that's 1/9. So we're going to have this over 9. And instead of u, well, u was sine theta. So I have sine theta cubed plus c. But the problem was still not about theta. So we need to put it back in terms of x. So it's going to be sine cubed of 3x, right, instead of theta, over 9 plus c. Alright, cool. So that was n. Now, that was a lot of u substitution with definite integrals. So let's see what would happen with definite integrals. But before that, we must discuss this theorem. This theorem is the change of variables for definite integrals. Alright, so this is what the theorem says, right? It says if the function u equals g of x has a continuous derivative on the closed interval from a to b, and f is continuous on the range of g, then we get the following. The integral from a to b of f of g of x dx is equal to the integral from g of a to g of b of f of u du. Alright? So what is this really saying? Well, what this is saying is, if I want to change this inside, this g of x, to be u, well, since our variable integration was in terms of x, well, our definite integral here, our bounds, should also be in terms of the new variable, which is what this is doing, this g of a and this g of v. So let's look at an example. And I forgot what letter we read. N. So O. So let's say that I said to evaluate the following. The integral from 0 to 1 of x times x squared plus 1 cubed dx. Well, we're going to start this in the same way as before. And you know what? Let's change this. Let's go from 2 to 5. Alright, exciting stuff. Now, in here, I want to let this inside here be our u. So u is equal to x squared plus 1. So that du would be 2x dx. Right? And this tells us now that dx is equal to du over 2x. Alright, so now, what does that do? Well, this is going to change our integral now. So we're going to get the integral of, hold on, this 2 and this 5. Those are in terms of x, and we just said we need to put things into terms of u. So when x equals 2, what happens with u? Well, put 2 into here. 2 squared, 4, 4 plus 1, 5. So when x equals 2, u is 5. When x is equal to 5, what is u? We'll plug in 5 into here. 5 squared, 25, plus 1, 26. So what do we get now? Well, originally the integral was from 2. Now it's going to be from 5. Originally it was up to 5. Now it's going to be up to 26. Of what? This x, not part of our substitution, still there. This x squared plus 1, that was our substitution. And we have that cubed. And now this dx is du over 2x. At that point we see that this x, did not mean to erase it, we see that this x and this x cancel each other out. So we get now 1/2 integral from 5 to 26 of u cubed du. And what is that? Well, that's going to be 1/2 times, add 1 to the exponent, divide by the new exponent, evaluate it from 5 to 26. And well, what would that give us? Well, that would give us 26 to the 4th over 2 times 4, which is 8, minus 5 to the 4th over 8. And at that point, well, let's see, 26 to the 4th. 26 to the 4th is a huge number. 456,976. And we have this over 8 minus, so 5 to the 4th. 5 to the 4th is 625. And now, 456,976 minus 625 ends up being 456,351 over 8. And that doesn't reduce nicely. But I will tell you this is approximately, actually this is actually equal to 57,043.875. But we like that. We don't really like decimals. We like fractions better. Alright? Alright. I do want to make a point here before we continue. In here, we did put everything into terms of u, so that we can have our bounds in terms of u and not have to worry about changing things back into terms of x. But we could have put things back into terms of x if we wanted to. So what I'm saying is, let's look at this one again. So we had the integral from, what was it, from 2 to 5? Yeah. The integral from 2 to 5 of x times x squared plus 1 cubed dx. Right? And I mean, we started the same way, we do the same exactly substitution, but instead of finding the bounds, we're going to say, well, so I'm going to go straight into this version here. Let's see how it changes. So I'm going to have 1/2 integral of u cubed du. And if you don't want to find out what the values, what the new bounds should be, then that's fine, as long as you keep track of the original variable. So in here, we're going to say from x equals 2 to x equals 5, all right? Because we have to make sure that we don't plug it into u. We need to plug it into x. So at this point, we say, well, we end up with 1/2 times u to the 4th over 4. Well, we already know that that's really u to the 4th over 8, and then it's evaluated from x equals 2 to x equals 5. And then, well, what was the value of x? Excuse me, what was the value of u? U was x squared plus 1. So I have x squared plus 1 to the 4th over 8 and minus x, well, evaluated from 2 to 5. And at that point, now I plug in the 5. So I have 5 squared plus 1. Well, 5 squared, 25 plus 1, 26. So I have 26 to the 4th over 8 minus plug in 2. 2 squared is 4 plus 1 is 5. So I have 5 to the 4th over 8. And I mean, that's what we had at this point, right? So we already know what the answer is. So I'm not going to continue from there. But my point here is that if you don't want to figure out these values over here of u, you don't necessarily have to, as long as you make sure to put things back into terms of x before you actually evaluate your definite integral. I will say I highly recommend that you get into the habit of changing things into terms of u, all right? In general, that's what I will be doing throughout all the examples, all right? But I did want to mention that there's this alternative. But anyway, so that was O. P. So let's say that we have the integral from 1 to 2 of 2x squared times the square root of x cubed plus 1 dx. Right? So in here, well, what does this do? I'm going to make our u be x cubed plus 1. So u is x cubed plus 1. So that our du is 3x squared dx. That gives us that dx would be du over 3x squared. The next thing, I need to change my bounds. So we have x being 1. So when x is 1, u is equal to, we'll plug it into here. 1 cubed, 1 plus 1 is 2. Let's figure out what happens when x is 2 for our upper bound. 2 cubed, 8 plus 1, 9. So we have u is equal to 9. And at this point, well, what does this integral become? We have the integral from originally 1, now it's 2, to originally 2, now it's 9, of 2 x squared. X squared I didn't use for my substitution, so it's still there, times. Instead of squared, I'm going to write it to the power of 1/2. X cubed plus 1, that was my substitution. Dx, we said that was du over 3x squared. And at that point, we see that the x squares cancel each other out. So what I really have here is 2/3 times the integral from 2 to 9 of u to the 1/2 du, right? These 2/3 coming from these 2 and that 3, put it on the outside of the integral. And at this point, well, what does this give us? Add 1 to the exponent, so u to the 3/2, divide by the new exponent, which really means multiply by the reciprocal of the new exponent. So what we really get here is, oh wait, hold on, my balance, from 2 to 9. So we get here is 4/9 u to the 3/2 evaluated from 2 to 9. And now that we're evaluating this, all right, we get 4/9, well, let's plug in the top. 9 to the 3/2 minus 4/9 times 2 to the 3/2. Notice here that we have 4/9 on both of these. So really, if we really wanted to, we could factor that out and write it this way, right? 9 to the 3/2 minus 2 to the 3/2. right? And what we can do is, well, at this point, what do we get? We get 4/9 times 9 to the 3/2. Well, 9 to the 1/2 is 3, and 3 to the third is 27, minus 2 to the 3/2. Well, 2 to the 1/2 is the square root of 2, and that to the third, well, this isn't really reduced nicely, but we can write it as 2 radical 2. And I mean, that would really be the final answer there. I guess if you really wanted to come up with a common denominator and distribute, we could, but I'm going to leave it as that. Right? So that was P. Q. Let's say I have the integral from 1 to 9 of 1 over the square root of x times 1 plus the square root of x squared dx. Right? So in here, I want to make 1 plus x squared, 1 plus radical x. I want to make our u. So we have u is equal to 1 plus the square root of x. I'll write that as x to the 1/2. Then what's du? Du would be, well, the derivative of 1 is 0. The derivative of x to the 1/2 is 1/2 x to the negative 1/2 dx. In other words, we can rewrite this as du is equal to 1 over 2 times the square root of x dx, which really tells us that dx is equal to, we'll multiply this up here, 2 times the square root of x du. And at that point, well, we still need to figure out our new bounds. So let's look at that. So when x equals 1, u equals, well, let's see, the square root of 1 is 1, plus 1 is 2. And when x equals 9, what do we get? Well, let's see, the square root of 9 is 3, plus 1 is 4. So now our new integral is going to go from 2 to 4 of what? Well, this one is there. This square root of x, that wasn't our substitution, so that's still there, times 1 minus radical x, that was our substitution, so we have that squared. This dx was 2 radical x du. So at that point, we see that the radical x's cancel out, and we end up with 2 times the integral from 2 to 4 of u to the negative 2 du. Right? Brought this 2 to the outside, brought this u squared to the numerator. And at that point, we get, well, 2 times, well, add 1 to the exponent, divide by the new exponent, evaluate it from 2 to 4. I'm going to rewrite this as negative 2 times 1 over u. Well, I guess I could use right then, negative 2 over u. Evaluate it from 2 to 4, which gives us, well, let's plug in the top. So that's going to be negative 2 over 4 minus, plug in the bottom, negative 2 over 2. So negative 2 over 4 is negative 1/2. And then minus negative, well, 2 over 2 is 1. So we have negative 1/2 minus a negative 1. So it's negative 1/2 plus 1, which is 1/2. Cool. Next one. So that was Q. R. Let's say I have integral from 0 to 1 of e to the negative 2x dx. Well, I want to say, well, let u be negative 2x. Then du would just be negative 2 dx, so that dx is just du over negative 2. At that point, well, we need to change our bounds too. So when x is equal to 0, what's u? Plug in 0, it's 0. When x equals 1, what's our u? Well, plug in 1. Negative 2 times 1 is negative 2. So now, what does that give us? The integral from originally 0, still 0, to 1, now it's negative 2, of e to the negative 2x, that was our u. This dx is du over negative 2. So we could really rewrite this as, well, put this negative 2 on the outside, negative 1/2 times the integral from 0 to negative 2 of e to the u du. But notice here in our bounds we have the top value being smaller than the bottom value. So what we can do here is we can flip those bounds by negating this integral. So we have really the positive 1/2 integral from -2 to 0 of e to the u du. And the integral of e to the u is just e to the u. So we have 1/2 e to the u. We value it from -2 to 0. So that gives us 1/2 times plug in the top, e to the 0, minus plug in the bottom, e to the -2. E to the 0, however, is 1. So we can say here our final answer is 1/2 times 1 minus e to the -2. Right? So that was R. S. Let's say I had the integral from -3 to 0 of x squared times the square root of 1 minus x dx. Alright, so let's see. In here, right, we normally try to look for something that whose derivative is somewhere else. But in here, this x squared on the outside, even though its derivative kind of looks like this inside here, right, the derivative of a quadratic is linear, that would be wrong to do here. So let's actually start with the inside being our u. If I let u be 1 minus x, then du is just negative dx, so that dx is negative du, right? What else? Let's see. We need to change our bounds. When x is equal to -3, u would be, well, 1 minus -3 is 4. When x is equal to 0, u would be 1 minus 0 is 1. So what does that give us? That gives us the integral from originally -3, well, now it's 4, to originally 0, now it's 1. This x squared, we didn't use it for our substitution. The square root, I'm going to write it as to the power of 1/2. And this 1 minus x, that was our substitution. This dx is negative du. Notice here that we still have an x squared. So what do we do? Well, what we can do is we can manipulate this over here. This is really saying that, well, if I solve for x would be 1 minus u, right? Move the x to the right side, move the x to the left side, move the u to the right side. So I end up with 1 minus u, which tells me that x squared is equal to 1 minus u quantity squared. So that's what we're going to do here. Let's apply this negative. That's on the outside, so the negative integral from 4 to 1 of x squared, which was 1 minus u quantity squared, times u to the 1/2 du. Our bounds, the top value is smaller than the bottom value, so let's change that, and we can do that by negating the entire integral. It's already negative, so it becomes a positive. The integral from 1 to 4 of, let's expand this. 1 minus u squared is 1 minus 2u plus u squared, and we have that times 1, u to the 1/2 du. If we distribute this u to the 1/2, what does that give us? The integral from 1 to 4 of u to the 1/2 plus 2, that plus minus 2u to the 3/2 plus u to the, well, this 2 is the same thing as saying 4/2, so 4/2 plus 1/2 is 5/2 du. And at that point, well, we know how to integrate this. So the integral of u to the 1/2 is u to the 3/2 times 2/3, right? Divided by the new reciprocal, but that's multiplying by the, what? Dividing by the new exponent, that's the same as multiplying by a reciprocal here. So we have minus 2 times u to the, add 1 to the exponent, 5/2, divide by the new exponent, so that means multiply by the reciprocal, so I'm going to write this as 5/2 times u to the, what? That's not good. Let's start that again. Add 1 to the exponent, u to the 5/2. Divide by the new exponent, it's the same as multiply by the reciprocal. There we go. Plus, add 1 to the exponent, u to the 7/2. Divide by the new exponent, multiply by the reciprocal. But this is evaluated from 1 to 4. So Well, let's see what happens. Let's plug in the 4. So we have 2 times 4 to the 3 halves over 3 minus, well, 2 times 2 is 4. So 4 times 4 to the 5 halves over 5 plus 2 times 4 to the 7 halves over 7 minus, plug in the bottom. We're going to end up with 2/3 minus 4/5 plus 2/7, right? Because in here, 1 to the any power here is just 1, so we just end up with those things there. At this point, I'm going to skip a few steps. I'm going to let you figure the work here in the middle, but I will tell you that this becomes 1717 over 105. Alright, so you should finish this problem so that you can verify that that's what you get. Alright, one last thing I want to talk about here as far as this section goes is this next theorem. And the theorem says, it is called the integration of even and odd functions. Even and odd functions. So here's what we have. If f is an even function and then the integral from negative a to a of f of x dx is equal to twice the integral from 0 to a of f of x dx. Recall here that even meant that f of negative x is equal to f of x. This is also saying symmetrical about the y-axis. Alright, so that's for even functions. Alright, now let's see for odd functions. If f is an odd function, then the integral from negative a to a of f of x dx is equal to 0. Right? And recall here that the definition for an odd function is that f of negative x is equal to negative f of x. Right? And this is saying symmetrical about the origin. Right? So it has rotational symmetry. Alright, so let's see. What letter was I at? S, I think? Yeah, good job me for remembering. C. So let's say that I had the integral from negative pi over 2 to pi over 2 of sine of x dx. Alright? Well, let's see. Sine is an odd function. So because we're going from negative a to a of an odd function, right away I can say this is 0. Done. Didn't have to integrate, didn't have to evaluate. It's just 0. U. Let's say that I had the integral from negative 10 to 10 of something like this, 3x squared plus 4 dx. Right? Well, this is an even function. Right? This is an even function. So what we can say here is we end up with twice the integral from 0 to 10 of 3x squared plus 4 dx. And the great thing about this is that now when we go to evaluate, there's going to be less calculation. So let's see what we get. We have 2 times the integral of 3x squared is x cubed plus the integral of 4 is 4x. And we have this evaluated from 0 to 10. So what happens? Well, this 2 I'm going to put on the outside. Plug in the 10. 10 cubed plus 4 times 10. And then that minus plug in the bottom. So 0 cubed, so that's 0 minus 4 times 0 is 4 plus 4 times 0? Let's choose 0. Alright, so this piece goes away. Cool. And what do we have? Well, 10 cubed is 1,000. 4 times 10 is 40. 1,000 plus 40 is 1,040. 1,040 times 2 is 2,080. So that's what we get there, 2,080. And again, here we did a lot less evaluation when it came to plugging in stuff, right? Because we can just go ahead and say the bottom part is really 0. Let's look at another one. So that was u, v. Let's say I had the integral from negative 1,000 to 1,000 of 15 x to the 19th minus x to the 13th plus 3x to the 9 plus 7x to the 5th minus x cubed plus 189 dx. Alright, now in here, this is an odd function. How do I know it's an odd function? All the exponents are, oh, hold on, I messed up here. That should be 189x. There we go. All the exponents are odd, right? 1, 3, 5, 9, 13, 19. That's just the thing that happens with polynomials. If you have a polynomial where all the exponents of x are odd, well, it's an odd function. And in this case, well, we're going from negative a to a. By the way, I know that's 0. Alright.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.